Hi everyone, and welcome to our unit on basic chemistry. In this unit, we're going to cover just enough chemistry so that we can apply these really important concepts to the biology that we'll be studying this year. What is everything made of? Floors and walls, vinegar, dogs, grass, mice. This is defined as anything that has mass and takes up space. It's matter, of course. It's what's all around you in liquid, solid, and gas form. The smallest unit that an element can be broken down into and still have all of the properties of that element is called an atom. Remember, the smallest unit of living life is the cell, but even cells are made up of atoms. Elements. An element is a substance that cannot change into a simpler substance. It's not to say that elements aren't made up of things or atoms aren't made up of things, but those parts that they're made up of don't have properties such as combustibility or malleability. They can't be metals or nonmetals until they have their protons, neutrons, and electrons all grouped together. All matter is composed of atoms. Numbers 1 through 92 on the periodic table are natural. Just in case you're wondering what number 92 is, it's uranium. And if you don't know what number 1 is, it's hydrogen. Anything past number 93 is synthetic or created in a lab. Essential. For something to be alive, it needs to have carbon, hydrogen, oxygen, and nitrogen. Most of them also have phosphorus as well. There are trace elements of things like copper, magnesium, and iron. All of these things make up organic matter. The atom. The atom is the most basic unit of matter. It has 3 subatomic particles: protons, which are positively charged, neutrons, which have no charge, and electrons, which are negatively charged. Every single atom on the periodic table is neutrally charged. This means that the number of protons and the number of electrons are going to be equal. Atoms like to be neutrally charged or have no charge. Here's a really simple atom. Now, full disclosure, electrons don't actually orbit the way that they're shown in this picture, but for our purposes, understanding this is enough. We just want to know that those electrons exist in a region of space that is close to the nucleus. Again, if we look at the nucleus of the atom, the green things are the positive protons, the red things are the neutral neutrons. These are held together by the strong nuclear force. Out here on the edge, we have electrons. The electron cloud orbits in the space around the nucleus. If there were more than one electron ring, the outermost one would be called the valence ring. The force that keeps the electrons orbiting around the nucleus is the weak nuclear force. Okay, remember how I said that there can be more than one electron ring? We want to be able to count how many electrons should be on those rings. On the inner ring, or the one that is closest to the nucleus, we have a maximum of 2 electrons possible. When we get to the next ring, we have a maximum of 8 electrons. Atoms love to have 8 electrons on their valence shell. Then if we had a third shell, in the elements that we're going to talk about, they hold up to 8 electrons. Full disclosure again, if you get higher up on the periodic table, more and more rows up, sometimes they can hold more than 8. But for our purposes, we're just going to remember 2, 8, 8. 2 on the inner, 8 on the next, 8 on the third. Whenever you look at a box on the periodic table, and we'll get to a lot more about the periodic table later. You want to be able to understand what each of these items are really about. So let's take them one at a time. We're going to start with this big number in the center. This is called the atomic number. It's also equal to the number of protons and the number of electrons for any block on the periodic table. Sometimes atoms are going to change the number of electrons that they have or the number of neutrons that they have, but not the ones on the periodic table. On the periodic table, the protons and electrons are always going to be equal. Let's go down. What's this big C? That's going to be the chemical symbol. Sometimes when you look at a really stripped down periodic table, they won't even have the full name. They'll just have this C because scientists know that that C equals the element's name, which is carbon. Now let's do the number at the bottom. It's a decimal number. And the reason that it's a decimal number is because it is the average mass of every carbon atom on Earth. So just imagine that you could get all the carbon atoms and you could add up all of their masses and then divide by the total number of carbon atoms that there are. On average, a carbon atom weighs 12.011. Now, the tricky thing is that when you're looking at any individual atom, you can't have this little decimal number hanging off the back because atoms can't have a part of a neutron. So when you do your math to figure out your neutrons, which we're going to talk about in a moment, you want to make sure that you're always rounding to a whole number. What's the atomic mass again? It's going to be the weight of the carbon atom, and it is protons plus neutrons. I want you to look at this for a moment, and I want you to think about if you could fill in this information. There's just one thing more that I have to tell you. When you do your number of protons, you just take your atomic mass and you subtract it from your number of protons. If you need more time, you can pause the video because I'm going to give you the answers on the next slide. Here we go. The element name is magnesium. It's Mg. The atomic number is always that big number, so even though it's not quite centered on this one, it's 12. The atomic mass is always going to be that decimal number, 24.3050. Now we get into the subatomic particles. How many protons? Remember, it's the same as the atomic number. How many electrons? This is an element on the periodic table. The protons and electrons are always going to be equal, so it's 12 too. The neutrons, remember we subtract atomic mass minus atomic number. So that's going to be 24.3050 minus 12. That gives us 12.3050, which when we round according to the normal math rules, gives us 12 as well. Then we go up here and we look for our valence electrons. We have 2, 8, and 2. So this last number 2 here relates to the number of valence electrons. Let's do one more example. I'm going to click to the next slide, and I'm going to show you arsenic. So just take a moment and think about this setup. If you need more time, just pause the video because it would be awesome if you all practiced. Again, the element's name is arsenic. It's As. The atomic number is 33. The atomic mass is 72.922. There are 33 protons, same as the atomic number, 33 electrons, because again, this is from the periodic table, so those two are equal. Then we get to the number of neutrons. This one's a little bit trickier. Remember, here's our atomic mass, 74.922. When I subtract 33 away from that, I'm going to get 41.922. Because in math we round up, we end up with 42. total neutrons, because remember, an atom can't have part of a subatomic particle. Then we get to the number of valence electrons, and we can go up here. 2, 8, 18, there's the last one, the number 5. If you want to double check and make sure that you're correct about your number of electrons, the other way that you can do the number of electrons is you can just add up all of these that are on each of the rings, and if you do, you'll add up to the number 33. So why are there all these different atoms on the periodic table? What makes one different from another? It's going to be the number of protons, neutrons, and electrons. But I'm just going to clue you in a little bit. The number of protons is really king here, because in a little bit, in the next lecture, we're going to talk about what happens when neutrons vary between elements and what happens when electrons vary between elements. So it's really the number of protons that makes carbon, carbon, gold, gold. Now, there are ways that you can change the proton number. You don't have to understand what that is right now, but if it changes, then the fundamental properties of that element change. Remember, magnesium had 12 protons and arsenic had 33. It's the difference between this proton number that makes one a reactive metal and the other a poisonous transition element. So for example, number 1 on the periodic table is hydrogen. If I added another proton to hydrogen, it wouldn't be hydrogen anymore. It would then be helium, because helium is the only thing on the periodic table that has 2 protons. Then if we added another proton, it would go to number 3, which is lithium. I know it seems odd, but you have to think about it as the protons being a fundamental property of an atom. It's as different as being a boy is to being a girl. What's the difference between that? Girls are XX sex chromosomes, boys are XY. So if you fundamentally change one of those chromosomes, you fundamentally change who that person is, what sex that person is. It's the same thing for the atoms. If you change the number of protons, you fundamentally change that atom. Okay, I told you that we were going to start to change some of the subatomic particles. So here we go. An isotope is an atom of an element that has a different number of neutrons from the normal. So let's go down here and let's take a little look. This is hydrogen. Every once in a while, hydrogen has only 1 proton in the center. It doesn't have any neutrons. Sometimes, though, it will have 1 neutron. Sometimes it gets really crazy and it actually ends up having 2 neutrons. So in nature, if you could randomly catch and look at a hydrogen atom, sometimes it would have just a proton, no neutrons. Sometimes it would have a proton and a neutron, and sometimes it would have a proton and 2 neutrons. This is fundamentally going to change the atomic mass of the isotopes. Let's look down here. This particular type of hydrogen, if you caught one with no neutrons, is going to have an atomic mass of 1. If you come over here, when it gets a neutron, it has an atomic mass of 2. And over here, it has an atomic mass of 3. But do you notice how it's still all hydrogen? I like to think about neutrons like the fluff in the cell. It's like the atom gaining and losing a pound. It doesn't fundamentally change what that atom is. That atom's just bulked up a little bit or thinned down a little bit. Probably the most famous example of isotopes in biology is carbon. And when we get along a little farther, when we start to talk about fossils and the fossil record, we're going to explain why carbon-12, carbon-13, and carbon-14 are so important. So don't worry, we're coming back to those. Isotopes, a little bit more. Sometimes isotopes can be radioactive, and when they are radioactive, they can be used in medicine. For example, Imagine that I had radioactive iodine. I can actually give that to an individual. That radioactive iodine will latch on to the thyroid, and it can actually make that thyroid glow on certain types of scans. So do you see how this person's thyroid right here is glowing yellow? This would allow the doctors to look at that thyroid. Is it normally shaped and sized? Does it potentially have a lesion? Could there be something wrong with this person's thyroid? Thus, it allows the doctors to make their treatment course. Sorry about that. I just skipped a screen. This is the last one to talk about in this topic. These are called ions. Ions are atoms that have gained or lost an electron. This makes them positive or negative. Remember, the particle we're talking about here is a negative particle. So, when an element loses an electron, it's losing something negative. It's called a cation, and that element is now positively charged. Excuse me, that atom is now positively charged. If an atom gains an electron, it's gaining a negative particle, so it's going to be negatively charged. Let's take a look at an example of each. Look at the atom on the left here. It says that it has 20 protons. If you were to count all of the electrons on the periodic table, it has 20, but this particular one only has 18. So this one has lost 2 electrons in some way. We'll talk about how that happens later on. But when it loses it, 20 minus 18 equals 2 plus. So this is a 2 plus ion of this element. Over here, this one says that it has 17. Normally on the periodic table, it would have 17 electrons, but this one doesn't. It has 18. So if you count up all of these little negative particles, you're going to find that there are 18. 17 minus 18 equals 1 minus. So this is a 1 minus ion. You might be wondering why elements would want to do this. They want to do it because in the next unit, we're going to talk about how they like to have their valence shell full. In other words, they like to have 8 electrons on their valence shell. When this one loses an electron, it now has when this one gains an electron, it now has a happy full valence shell. When this one loses the electrons that were on its outermost ring, its next ring in is full, and it has now a full outer valence shell. In the next chapter, we're going to talk more about the periodic table, and then we're going to use what we learned in this lesson plus the next lesson to understand why atoms would want to bond.